Hey everybody, it's Mr. Sheline here. This is going to be the Check Your Understandings for the 6.3 notes covering torque. So if you haven't already, make sure you go watch the torque lecture video if you were absent, or if you need to review anything before watching this. Make sure you watch that first, ask me any questions, and then come back to this. Complete the Check Your Understandings and then double check your work. So anyway, I'm going to get going on this now. So check your understanding number 1. A force is applied to a revolving door that rotates about its center. Rank these situations based on the magnitude of the torque experienced by the door, largest to smallest. So here we've got the axis of rotation right here. Actually, I'm going to zoom in just a little bit here so we can kind of have a better look at what we're doing. So I've got the axis of rotation right here for this door, and then also this door. So for this door, it's going to be moving counterclockwise. The force is being applied here perpendicularly. Over here on B, the force is being applied, again, in counterclockwise, but this time it's all the way at the end here, and we have to distinguish which one's going to have the greater torque. So remember, when it comes to torque, generally speaking, the further we are away from the axis of rotation, and also when we have a perpendicular force being applied, the greater the torque that will be put onto whatever object we're trying to rotate. So in this case, because on B, our force is all the way out as far as it can possibly go, we're going to say number 1 here, that the torque that the individual will be putting on B will be greater than the torque experienced at A. Okay, and then for check your understanding number 2, so a force is applied, basically it's the same thing. The only difference now is that A is still the same, but now we've got a force of C. Now, roughly speaking, I know the arrows here are like this arrow is smaller than this arrow. They really should be roughly about the same size. So imagine if they were the same size, what would be true here? And I'm trying to get this glare out. I don't know why I've got this nasty, nasty glare on the page. Maybe it's not as bad as I think it is. But anyway, what would be true? Would C be greater than A? Would C and A be somewhat equal to one another? Or would C be less than A? So thinking back to what we just went over, at least what was talked about in the notes, when we calculate the amount of force being applied when it's at an angle, what we need is actually the perpendicular force to calculate here. So it's going to, in this case, the torque is going to be calculated with F times D times sine of theta. So whatever theta is here, okay, we'd input that and say, well, the actual perpendicular force is actually this, that it's F times the sine of theta. So if this force and this force are roughly the same, okay, only this one's at an angle, fortunately this force will just end up being smaller. So in that case, we'll say C, or sorry, we'll say number 3, that C is going to have a lesser force applied to, or a lesser torque than A will, okay? All right, check your understanding number 3. Let's see here. Okay, so a student pushes with a minimum force of 50 newtons on the middle of the door to open it. And then the 2 questions here are, what minimum force must be applied at the edge of the door in order for the door to open? And B, what minimum force must be applied to the hinge side of the door in order for the door to open? So if we're looking at B, okay, if this is our door, so here's my hinge, so here's the hinge, and this is my door. Okay, well in A, let's see, or sorry, what's being set up here is the fact that a force is being applied in the center. Okay, we've got a force of roughly about 50 newtons here. So then the question is, well, if it takes about 50 newtons to push it when it's in the center, what's the minimum force amount needed to be out here? And so this one's fairly straightforward. It's the idea that, well, it took us 50 here, it's in the middle. If we increase the distance of our lever arm by basically if we double it, Okay, so instead of being halfway from, we'll say halfway in the center of the door, halfway from the distance from the axis of rotation to the very edge of our object. If we go from the center to the outside, we're just doubling the lever arm. And if we're doubling the lever arm, we don't have to put as much force. So it's literally just 50 divided by 2, which will be then 25. So at the minimum, when we apply a force all the way out here, we just at minimum have to apply 25 newtons. Then B asks, what minimum force must be applied to the hinge side of the door in order for the door to open? So it's to say that, well, how much force do we have to apply here in order to get this door open? Well, there's not a whole lot of distance from here to here, and though we could measure, what minimum amount of torque is needed, honestly, there really is no force great enough that's going to open the door here, okay? Unfortunately, in this case, if we were to maintain a perpendicular force, we would not be able to open up the door. So really, it's just 0. We can't open the door. Okay? Yeah, we can't open the door because the closer we get to the axis of rotation, the closer we get to it, and if we apply our force as close as possible, we need a whole lot of force to move it, and in some cases, in a lot of cases, you won't be able to move it. In a lot of cases, you're probably just going to end up breaking something first before you're able to actually do what you want it to do. Okay, so for B, it's going to be we can't open the door. For A, it's 25 newtons. Okay. Then we're going to get to check your understanding number 4, number 5, 6, and then 7. So a basketball is being pushed by 2 players during tip-off. One player exerts an upward force of 15 newtons at a perpendicular distance of roughly about 14 centimeters from its axis of rotation. The second player applies a downward force of 11 newtons at a perpendicular distance of 7 centimeters from the axis of rotation. Find the net torque acting on the ball. So first things first, to draw a picture of what this looks like. So 14 centimeters is going to be the radius of our basketball. Okay, so the radius here is going to be 14 centimeters. Okay, so it's the very outside. So we've got one player exerting an upward force of 15 newtons. Okay, so you could say that it's applying it like right here-ish. Upwards force of 15 newtons. Okay, and then the second player is a downward force of 11 newtons. Okay, it's going to be a downward force, and it's going to be somewhere like 7, it's like 7 centimeters, so it's like breaking the center, it's like in the middle of the radius. And here it's going to be a force of, what is it, 11 newtons? Of 11 newtons. Oops. So here for this force, the distance is 14 centimeters. Here the distance, the lever arm is going to be 7 centimeters. It's asking, well, what's the net torque? So here we don't know the torque over here, and we don't know the torque experienced over here just yet. And it's asking, well, what's the net torque going to look like? Okay, what's the net torque going to look like? So the net torque is dependent upon, it's dependent upon here the direction of the forces, and it's also going to depend upon exactly just how much force is being applied, and on top of that, so 3 things, the distance from the lever arm. So let's just do this one by one. Let's find the torque of this guy and then the torque of this guy. Okay, actually, no, the first thing we should do is determine the direction that they're moving, because that's a big impact. So if we look at this, if we ignore this force over here, and if we let just this force to work on the ball, what direction is this ball going to move? And it looks like if this guy were to push down on this ball, the ball would spin, presumably. The ball's going to spin counterclockwise. Okay, so this guy's counterclockwise, so we'll put like counterclockwise, just to like label that this is going to be counterclockwise. Okay, so now let's ignore this guy. If we were to push the ball over on this one, what direction would this be? It looks like this would also be counterclockwise. Okay, so it looks like my net torque here, because it's going to be working in the same direction being applied to this ball, since my torque is going to be in the same direction, my net torque should be you know, it's like we're going to add these two torques together. Okay, so let's see what we get. So first we're going to find the torque of this dude, which is just going to be easy peasy, just F times D. Okay, which in this case it's going to be 11 times 7. Oh, excuse the bell. Oh, and it's not just 7. I almost fell for this. It's not going to be 7. It's going to be 0.07. Okay, because we've got to have it in meters. Because remember, torque is measured in Newton meters, not Newton centimeters. So actually, it's 0.07. So 11 times 0.07. So it'll be, my torque's going to be like 0.77 Newton meters. Okay. What about my torque over here? Well, this guy, it's the same thing. Here's my force times the lever arm. So force is going to be 15 times not 14, but 0.14 meters, which that's going to give me 2.1. So because they're both moving in counterclockwise, and honestly, if you drew this picture flip-flopped, where you had where this was actually being applied like over here, this was being applied over here, it's the same difference. In that case, they'd be moving clockwise. Now, in the notes, I talked about if it's clockwise, then we make it negative. If it's counterclockwise, it's positive. So if you drew this in the clockwise position and showing that these are actually going to, the basketball is going to move in a clockwise direction, that's okay. In this case, your answer doesn't have to be negative. It'd be nice if it is, but if you indicate that it'll move in counterclockwise, that's good enough too. And I'll show you what I mean by that in a bit. So anyway, both these forces will make the ball move in the same direction, so we're going to just add them together. So my net torque is going to be torque of 1 plus torque of 2, which will just be 0.77 Newton meters plus 2.1 Newton meters, which this is going to give me a net torque of roughly about 2.87 Newton meters. Okay, now it's, oops, and I forgot to do the little thing. Not only is it 2.87 Newton meters, in this case, just because we were looking for the net torque, it's going to be that 2.87 Newton meters counterclockwise. Okay, so if you get, again, if you did it in clockwise, so if in clockwise, then your net force could look like this. It could be negative 287 Newton meters, or you could say the net force was 287 Newton meters clockwise. Okay. So you can make it look like either one and it'll be fine. If it's a negative, that indicates to me that it's moving in clockwise direction. If you keep it positive but then add the direction at the bottom or at the end like this, like we do with like north, south, east, and west, then that's fine too. But anyway, the net torque here would be 2.87 Newton meters. Number 5. Find the magnitude of the torque produced by a 3 Newton force applied to a door at a perpendicular distance of 0.25 meters from the hinge. So just to draw a picture here, boop, boop. So it doesn't really matter, well, just because of the way the door works and how simply we're looking at torque, it doesn't really matter the mass of the door nor the distance of the door in this practice. It's just, here's your lever arm. So we're going to say, here's our lever arm, where we're going to apply a force of 3 newtons. We're at a distance 1/4 of a meter away. What's the torque? Okay, torque is just going to be F times D. It's perpendicular, so we don't have to worry about sine of theta, because then it'll just be sine of 90, which is just 1. So it'll be 3 newtons times 0.25 meters, which will give us a torque here of 0.75 Newton meters. Easy peasy. Nothing else really to do here. Okay, super simple. Number 6, a simple pendulum consists of a 3 kilogram point mass hanging at the end of a 2 meter long light string that is connected to a pivot point. we've got to calculate the magnitude of the torque due to gravitational force around the pivot point when the string makes a 5-degree angle with the vertical, and then we have to just repeat that when our calculations are with 5 degrees. So what's happening here? Well, all that's happening here is that we have a pendulum, and we'll say the pendulum looks like this, okay? And here, this is when it's at equilibrium. It's not moving. It is not moving. It is not at an angle. It is perfectly level relative to the ceiling and the floor. So this is what it would look like resting. So the question's asking, well, if we were to take the same pendulum and if we were to, now this angle is a bit exaggerated here, as you can see. And if we make an angle here of, say, 5 degrees, well, how does that change the torque of the, that the, of this particular pendulum at 5 degrees? And then if we were to increase it even further, and I'm actually going to do it like this to make it a little bit, again, super exaggerated. If we then increase that to 15 degrees, what is the torque? So what's the torque here at 5 degrees? What's the torque here at 15 degrees? Okay. And so we have to first ask the question, exactly just what's our theta, what's our mass, and then what is the force that these pendulums are, or the pendulum here is experiencing or putting onto the wall, or I should say the ceiling. So in our first one, in the 5 degrees, so 5 degrees here, and this one over here will just be 15 degrees. So we've got a mass of 3 kilograms on our little dude here. It's hanging down roughly about 2 meters, oh goodness, 2 meters from, I put D is equal to 2 meters. And we're trying to figure out, well, what's the amount of force? Okay, we've got theta, 5 degrees. We're wanting to know, well, what's the torque? What's that torque going to look like? So because looking at our picture here, this force here is not being applied. Oh, excuse the bell. So here, the question may be, well, how do we know we're going to use the 5? How do we know that we are going to, why are we using the 5? How do we know we're going to use that? How do we know we're going to use the 15 degrees? Let's see. Basically the question is, why aren't we using this angle here? Why aren't we using this angle right here? Well, ultimately, in this case, we have a hanging mass. Its equilibrium is going to be the equilibrium of the ceiling is where the torque is being applied. So we're not calculating any torque that's on the pendulum per se. We're calculating the amount of torque the pendulum is putting onto the ceiling. So really you could think of it like, well, when it's at equilibrium, the force is pulling down, straight down. In this case, it's almost like the force is being pulled down in this direction and then in this direction, okay? And we're just comparing it to the equilibrium point. Now you could use this angle right here, okay, which would just be 45, okay? Or wait a minute, it wouldn't be 45, it would be what, 55? No, my goodness. Hold up, math is hard. Oh my God, this is embarrassing. That's 5 degrees. Oh, and my brain just turned off. Stop it, brain. No, this would be, it's got to add up to 180 inside here, so typically 45, but that's 5 degrees. Oh my God. So roughly speaking, this angle here, which is the same angle right here, would be, oh my God, why am I blinking so bad right now? This is pathetic. Oh my God. I have to draw a picture. This is 90 degrees. That's 45. That's 45 if it's nice and equal and balanced. So it all adds up to 180. So if I have one here, 95. 95 minus 180. Oh my God. So this guy would be 85 degrees right here. Okay. So why don't we use this 85 degrees? Jeez, I'm sorry about that, guys. That's pretty sad. Why don't we use the 85 degrees here? Why don't we use the whatchamajoots? It's just our reference point, and our reference point here is just in the vertical. If we were to use the amount of force based upon that, and actually we can just see if there is much of a difference. Which off the top of my head, I don't really think there's going to be. So if we do this, so I'm just going to do this real quick. 8. Okay. Let's see. Oops. That's going to compare it to 3. 9.8 times 2 sine of 5. Let's see. Oh, because let's see, calculate. Oh, it's because that's why. Because we're in reference because of the force is being pulled down rather than being pushed up. We go by the vertical. Sorry, I was just mentally thinking about why it is that, again, why we're using the 5. And it's because the reference point is that we're pulling down, due to the gravitational force, we're pulling down rather than pushing up on something. And in this case, because it is at an angle, we have to take into the account, again, against the equilibrium. And I basically already said that, but just to kind of reiterate it, that's why. Anyway. So if you got to pull it down, this is how we're going to do this, because the equilibrium point is what we're referring to as far as why we're taking a particular angle. Anyway, so first, what's the force? Well, the force is just going to be 3 times 9.8. So we can get the force due to gravity, which is roughly going to be 29.4 newtons. And that's going to be the same for both sides. Okay, still have a theta, but this time it's going to be 15 degrees over here. Our distance is still 2 meters. Mass is still 3 kilograms. What is our torque? So this one is, we set it up exactly the same. Force times the lever arm times the sine of theta. What's here? It's going to be 29.4 times d, which is 2 times the sine of 5, which is going to give us a torque of roughly about 5.12 Newton meters at 5 degrees, and then at 15 degrees, okay, because now all we got to change is 15 degrees, it's now going to be 15.2 Newton meters at 15 degrees. So quite a difference in torque as we, in this case, due to gravity, as we keep angling this bad boy out further and further. Okay. And then lastly, number 7. If the torque required to loosen a nut on a wheel of a car has a magnitude of 40 Newton meters, what's the minimum force that must be exerted by the mechanic at the end of a 30 centimeter wrench to loosen the nut? So here we have torque already given to us, 40.0 Newton meters. Okay, we've got a lever arm of 30 centimeters. How much force do we have to use? Okay, now it's implied here that the force being put onto this nut, which, just to make a quick drawing, it's going to look something like this. So here's my nut, and then here's the wrench. Okay, and so the distance from here to here is roughly about 30 centimeters. Okay, and if we're applying a force right here, how much force do we need to apply here if the minimum amount to put in is 40 Newton meters? Easy peasy. Just set up our torque. And it's perpendicular, by the way, if I didn't make that clear. Again, perpendicular. so we don't have to worry about sine of theta. Okay, so we're trying to solve for this guy, so it just basically turns into, well, force is equal to torque divided by d, by our lever arm. Which will then turn into F is equal to 40 divided by 30, which will then, easy peasy. Oh my goodness, second time I did this. 0.30 meters. My God. 40 divided by 0.3. So the minimum amount of force that we need to apply here is going to be 133 newtons worth of force. And that's it, guys. So that's Check Your Understandings. If you still have any questions for me, make sure you ask. If not, I'll see you in the next one.